So we'll take our quick look at the calendar. Today we're going to talk about derivatives of inverse functions. In particular, the inverse trig functions have derivatives, and we'll see a few of those. And last class we reviewed log functions, so today we'll see the derivatives of log functions. Next class is our derivatives overview. Nothing new really, but just giving you more and more complicated ways of putting together all of these functions that we now know how to take derivatives of. And then coming up on Friday is our review day for the test, which is scheduled for November 3rd, which I think is a week from today. Yes? Monday next week is our test number 2. It is definitely not too early to start studying for that test, 1 week away. And in the packet, if you just go towards the end, you'll find sample test problems, and there are videos about those problems on YouTube. So the same resources we had before, all there available in the packet and on YouTube and on Moodle. Also today, the steel drum project is due, so if you've got it, put it in the folders. The lateness penalties, I'll just remind you, if you don't have it right now, then but you give it to me by the start of Wednesday's class, it's 5 points off. If you give it to me after the start of Wednesday's class, within a week of right now, it's 10 points off. But a week from right now is the kind of firm deadline. So hopefully they're in the folders right now, but if not, get them in ASAP. And then coming up due Wednesday is the pipeline project. I do have your take-home quizzes. I'll give them back to you just in a few minutes. Questions on the calendar? Okay, so let's come back here to page 42. Just one quick note here, you might want to bring your textbook to next class. I think some of you bring your textbook every day, but next class, the activity is all in the textbook. So if there's not too much difficulty, make a note to yourself to bring in that textbook for next class. Okay, the daily summary, Petru. Thank you. Okay, that's good. And down here, number 1 in the demo, we saw this fact last class, that e to the ln of x is equal to x. That was one of several facts we saw with e's and logs canceling each other. And so here's what we're going to do. The goal of this problem right here is to find the derivative of ln of x. We don't have a formula for the derivative of ln of x, and that's what we're about to figure out. So we're going to use this fact that we established, like everybody believes that equation is true, right? That e and ln cancel, and we just get the x. So we're going to take the derivative of both sides of that equation. So let's give it a shot. All right, I'm going to do the derivative on the right-hand side because that's easier. The derivative of x is 1. So far, so good. Left-hand side is tougher, but in my mind, I see e to some stuff. So in English, what's the derivative of e to some stuff? It's e to the stuff, and then times the derivative of the stuff. That's our e rule. So e to the stuff we copy, times, and now the derivative of the stuff, so I'm just going to write it in symbols, but whatever the derivative of ln of x is what goes right there, right? And I don't happen to know that derivative yet, but this is how we're going to figure out what that derivative is. Does everybody see the e to the stuff times derivative of the stuff? Okay, let's clean this up. E to the ln of x simplifies. What is it? It's just plain old x. So this is really x times the derivative of ln, whatever that is. So apparently when I multiply, I get 1. And so we can then solve that equation for this thing right here, the derivative of ln of x. That's what we're after. What do we do to both sides to get that derivative by itself? As we divide both sides by x. And then we're left with the derivative of ln of x equals 1 over x. That's it. That's the derivative of the natural log function. It's 1 over x. And so down here in number 2, we get to fill in our brand new rule. Derivative of ln of x is 1 over x. Which means that we can use the chain rule to find the derivative of ln of stuff. What is it? 1 over the stuff, just like 1 over x, right? And then times derivative of stuff. That's it. So let's try number 3. Give us some practice with our new derivative rule for ln. So the first one is ln of some stuff. That's perfectly ready to go for our new version of the derivative of ln of stuff. So we go y prime equals, how do we start? Good. So we copy that stuff one time and it just goes in the bottom. That's always where it goes when you take derivative of ln. It's 1 over the stuff and then times, no longer in the bottom but next to the fraction, the derivative of what's in the parentheses, which is 3x squared minus 7. What am I missing? Parentheses, right? Because that 3x squared minus 7 is one thing. So the whole fraction gets multiplied by that derivative. That's it. Questions on the derivative of ln of stuff? Okay, part B, I see y equals ln of x to the 7th. Do you see ln of stuff in this case, or do we see a different version of the chain rule? Yeah, this is really what? How do I say this in terms of stuff? Stuff to the 7th. That's what this is, right? This is some stuff to the 7th. And if I have stuff to the 7th, that's my power rule. So what do we bring down? 7 times, and we copy the stuff. And the new power is 6. And that would be the answer if the original had just been x to the 7th. It would just be 7x to the 6th. But in this case, you again have to pay for it times the derivative of the stuff in the parentheses, which is 1 over x. That's it. Okay, so got some experience now with the ln derivative. We're going to learn a brand new derivative formula next, and it's going to be the derivative of the inverse sine function. The derivative of the inverse sine function. And so to get the derivative of that, I'm going to take the derivative of both sides of an equation, which I believe to be true. Do you guys buy that if you have sine of inverse sine, then they just cancel and you're left with whatever was in there? And that's the definition of inverse sine, is it's meant to cancel the sine function. So I'm going to take the derivative of both sides of that equation. Okay, so here's what I see. I see sine of stuff equals x. You guys buy it? It's just sine of some stuff. So we don't need to get thrown off by what's in the parentheses. It's just some stuff. So what's the rule for sine of stuff? What's the derivative of sine x? It's cosine x. So the derivative of sine stuff is cosine of the stuff times derivative of the stuff. So let's write that. So derivative of both sides. So we go cosine of the stuff times, oh, I don't need to write stuff. Cosine of what is this stuff in this case? Inverse sine times derivative of the stuff. And again, the stuff is inverse sine x. What's the derivative of the right-hand side? Just 1. Any questions on the left-hand side so far? We had sine of stuff. Derivative of sine becomes cosine times the derivative of the stuff. Okay, again, the goal here was to find the derivative of inverse sine of x. Well, I see that expression sitting right here. So really all I need to do is get that thing by itself and I'll have my answer, right? We don't know what the derivative of inverse sine is. We're about to figure out what the derivative of inverse sine is. So what do we do to both sides to get this green thing by itself? Divide by that messy cosine of inverse sine x. So let's do that. And so we get the derivative of inverse sine is equal to 1 over cosine of inverse sine of x. Okay, so we've got our answer. The derivative of inverse sine is 1 over cosine of inverse sine of x. It's correct, but typically we don't write the derivative of inverse sine this way. We know that cosine and inverse sine they don't cancel each other, right? Because they're not matched up perfectly, but they do work together in a certain way. And so what we're going to do is like a pre-calculus thing on the side to make it so that we have something that's a little bit more familiar looking in the bottom, because cosine of inverse sine, like they combine, like I said, but it's really not clear what they combine to. So here's what we're going to do. The goal is to just clean up that thing in the bottom. So I'm going to start by just saying let inverse sine of x equal theta. And I think that's a good name for it because the inverse sine always spits out an angle, right? Like you ask for the inverse sine of 1 and it says, oh, when is the sine up at the top? Oh, it happens at 90 degrees, pi over 2. So it spits out an angle. So I think calling it theta is a good thing. And so if we just take the sine of both sides, then that really means that the sine of theta is x. Just sine of both sides. So it cancels the inverse sine on the left and we just get that. Okay, now typically in terms of right triangle trig, we know that sine, I'm just going to draw like this kind of arbitrary right triangle here with a theta and a right angle. We know that sine is what over what? Opposite over hypotenuse from SOHCAHTOA. So let's force this x to be a fraction by making it x over 1. Okay, so we know that sine is supposed to be the opposite over the hypotenuse. So that means that, where am I putting the x? It's on the opposite side, so we'll label this guy over here as an x, right? That's the opposite. Where does the 1 go? On the hypotenuse. What famous theorem can we use to fill in the other leg? Pythagorean theorem. So I'm just going to write the answer. It might take an extra step for you to go through the calculation, but you will get square root of 1 minus x squared from the Pythagorean theorem. And so then when it comes to, so we got this kind of random triangle here. So how does that help us? Well, look at what we were after. We were trying to find a simpler way to write cosine of inverse sine of x. But I renamed this thing in the parentheses. What did I call the inverse sine of x? I called it theta. It's the very first thing I did. So really, this problem is about finding the cosine of theta. But if you have a right triangle with all the sides labeled and a theta, then you can read the cosine of theta. What over what? For cosine. Adjacent over hypotenuse, right? So we look at the adjacent side and we divide by the hypotenuse. The adjacent side is, so I'll just copy the one that's upstairs. And then the adjacent side is this root 1 minus x squared divided by hypotenuse 1. So just 1 over root 1 minus x squared. And that is our answer for the derivative of inverse sine of x. It's 1 over the square root of 1 minus x squared. So any kind of murkiness that you have in your mind right now for that derivation it's about the pre-calculus. The calculus was really easy. The pre-calculus is this kind of invented triangle that we bring up just so that we can simplify cosine of inverse sine. But we did, and we got our answer, 1 over root 1 minus x squared. And so then this gives us another opportunity for the chain rule. So what's the derivative of inverse sine of stuff? So normally it's 1 over root 1 minus x squared. It becomes 1 minus stuff squared. Right? We just change the x into some stuff. And then again, we pay for it times derivative of stuff. Okay, so I know that probably that's the most complicated derivative rule we've seen, but like don't worry about it. I mean, at some point if you have it memorized, great, but if not, it can always go on your index card before you take a quiz or on your kind of your sort of cheat sheet when you take a test. So the important thing isn't that we have these rules memorized, but that we understand that the rules are there and we know how to use them. So one more rule for right now, last one for today, is to find the derivative of inverse tan of x. I'm not going to go through the process, but it's similar to the one we just saw. Turns out the final answer is 1 over 1 plus x squared. That is the derivative of the inverse tan. There's no reason for you to believe that that's true other than me saying, hey, if you do the calculation similarly to what we did before, this is what you will get. But that means we can apply our chain rule now. So inverse tan of x becomes 1 over 1 plus x squared. How about inverse tan of stuff? 1 plus 1 over stuff squared times derivative of stuff. Okay, so let's bring all of our new rules together and try to find the derivative of this beast. Inverse sine of 5x over arctan of x cubed. So first, arctan is another way to just write what? Inverse tan, right? So it's just the same thing. Okay, what rule do we need to apply first and foremost? It's a quotient rule, right? Again, kind of like blur your eyes a little bit so you can't see all the details other than the fact that this is a fraction, which means quotient rule. So derivative equals, I always start my quotient rule by putting the bottom because I might forget to put it when I get lost in doing the top calculation. What goes in the bottom? Yeah, so we take the whole thing that was in the bottom, we square it, right? That's the new bottom. Okay, so in English, I know the quotient rule as bottom times derivative of the top. So I'm going to copy the bottom. And then multiply by the derivative of the top. So I'm going to put this in another color here, but what we're looking for right there is the derivative of inverse sine of 5x. But we saw inverse sine of stuff right on the previous page. So inverse sine of stuff is 1 over square root of 1 minus the stuff squared. 1 over square root of 1 minus some stuff squared. What's the stuff? It's 5x. But then we're not quite done because the chain rule always comes in and says times the derivative of the stuff. What's the derivative of that 5x? 5. So that right there. So all of this is the derivative of inverse sine of 5x. Now we'll keep going with the quotient rule in a moment, but I just want to point out that even though the derivative of inverse sine has a square root, and even though it becomes a fraction, that doesn't mean you're applying the quotient rule to this fraction, and doesn't mean you're applying, like, you don't need to rewrite that square root as something to a half power and then take the derivative of that. It's just part of the definition of the derivative of inverse sine. It just looks like a fraction with the radical in the bottom. Okay, so again, quotient rule says bottom times derivative of the top. What's the next word? Minus top times derivative of the bottom. So we'll copy the top. And then we need to multiply by derivative of the bottom. So all this stuff right here is supposed to be derivative of arctan x cubed. So we said that arctan is the same as inverse tan. I see right here in green at the top of this page the derivative of inverse tan of stuff, 1 over 1 plus stuff squared. So what does that become in this case? One over 1 plus x cubed squared. That's it. Okay. Stuff is just x cubed in this bottom part. But then times derivative of the stuff. The stuff is still x cubed, even though it might look like x to the 6th. X to the 6th is just part of the rule here, but x cubed is the stuff. What's the derivative of that stuff? 3x squared. So that is the derivative. A thing of beauty. It's all relative, I guess. Questions on that? Okay, so a quick overview of the activity which you're about to start. You're going to find the derivative of log x. We did ln of x, that was what we did to start today, but you'll find the derivative of regular log x, and then you'll use it with the chain rule. You'll look at an example involving decibels. And on the next page, there's this kind of funny example with a spotlight moving up and down a wall. There's an angle involved, and all of a sudden, one of these inverse trig functions is going to come into play. And then you'll actually prove something that I just asserted earlier today, that the derivative of inverse tan is 1 over 1 plus x squared. So you will prove that, and then there's the answer key. So give it a shot. I will walk around and take questions.